Good morning, everyone. Thanks for the introduction, and I should also thank the organizer of the conference for inviting me to be here, to be at this very nice city of Lugano, where you have a lake to walk around, to cycle around, to swim in. And also you can climb up the mountains to get a very different view of the lake. So as you can see, I'm from the National Supercomputing Center in Wuxi. We also have a pretty big lake by the side of our center. The pity part is we can't swim in the lake. I will explain why afterwards. And also I'm from the Department of Earth System Science in Tsinghua. So that's part of the reason I'm talking mostly about climate and weather in this talk today. Okay, so first I still want to spend a few minutes to introduce to you the machine. I guess many of you have already known the major features. I still would like to go through some of the best parts. So first, the lake. The lake is very important. I was so excited when I learned about from Zurich, actually from Thomas, that you can actually swim in all the lakes in Switzerland. Very different from China. So this is actually the name of our computer, Sunway, which is these two Chinese characters literally means the power of the God. And the name of the exact machine, TaihuLight. So Taihu refers to these two characters. So as I mentioned, so these two characters actually literally means super large lake in Chinese. As you can see, it's roughly the same size of the city of Shanghai. So it's a very big lake. And okay, so the reason that we put it in Wuxi, this is the zoom out version of the lake, as you can see, is actually in history, maybe from like 1,000 years ago, it's already the most developed areas in China. And as you can see, still for today, it's very, I should say, it's very dense with all these, cities, highways, high-speed train roads, and as you can see, these cities, I put a list here. So similar to top 500 list in supercomputers, we have a list of cities, well-developed cities in China. So these cities are all among this list. So this is, as you can see, this is an area with a lot of economic activities going on. So one thing I want to mention here, in China, the supercomputers have to live on their own, which means, you have to earn the electricity and all the maintenance cost to keep it going. So this is very important. I mean, we're in an area with enough industry potentially to support it and also to, to benefit from this very large system to get a cycle that can actually goes on. Okay, so as I mentioned, the Sunway is actually a series of machines. So this is a little bit about the history of Sunway supercomputers. So the first Sunway computer was actually born in the year of 1998. Now the reason is because 1 year after 1999 is the 50-year birthday of the People's Republic of China. And some of you might remember there's this very big, great parade going on Tiananmen Square. And to do that, they need very accurate weather forecasting. So that's the reason that they built up this very first system for weather forecasting services. And the second system, Blue Light, in the city of Jinan, which you can consider as the truest generation of TaihuLight. So actually, these two systems, they share a lot of similarities, I should say. The first part is in the design of these cabinets. As you can see here, if you have been to our center, these computing cabinets, they're actually organized as a circle. So it's a circle of machines rather than normally rows or columns of machines. And the other part is about the processor. So they actually, these two generations of processors, both of them are organized as 4 core groups. Now the difference is, of course, for the Blue Light is a multi-core thing. Each core group only have 4 homogeneous cores. But for this TaihuLight, where you have more cores. Each core group actually have 65 cores. So 1 management core and 64 computing cores. So this actually shows some more information about this processor architecture we use in Sunway TaihuLight. As I mentioned, 4 identical core groups, and each of them has one what we call MPE, management processing element, which is more like a traditional CPU core, where you can do management, communication, computation. And we also have this computing core, which we call CPE, organized as an 8x8 mesh, where you have both buses for rows and columns, where you can exchange information very quickly among these different cores at the level of registers. So that's kind of a different design in this processor. Above the processor, we have very high density when we actually integrate it into a supercomputing system. We call it a 5-level integration hierarchy. So this is the first level where you have a small computing board with 2 processors. So that's like 2 nodes in our system. And then you have 4 of them, so 2 at the top. We don't have the bottom ones in the animation. So 2 at the top and 2 at the bottom. So that's 4 computing boards and 8 computing nodes in just this one larger board. And then we have 38 of them to goes into this super node, what we call a super node, which is 32 computing boards, 256 processors. The reason we call it a super node is because we actually have a customized network board sitting behind to achieve fully connected interconnection among these different nodes. And above that, we have 4 cabinets, 4 of them to form a cabinet and 40 cabinets to form the entire computing system. So, okay, so this is the math for over 10 million cores, how we get there and how we actually interconnect all these guys. 65 cores per core group, which are connected by this, as I mentioned, row and column buses, and then 4 of them to form a processor with the network-on-chip interconnection. And then we have 256 of them in one supernode. 4 by that is over 1,000 in just one cabinet. So one cabinet already provides a performance of roughly 3 petaflops. And then on top of that, so on top of the supernode is what we call a Sunway net. Is pretty much the same as other supercomputer systems, a factory architecture to connect all these different things. Okay, to end the introduction about this machine, I'd like to quote some tweets from Professor Satoshi Misaka. I guess many of you also know him quite well. So early November last year, he visited our center to take a look at the real machine. And of course, Professor Misaka is, very excited about tweeting. So on the second day, he was so excited, he actually sent out 4 tweets and commented on this system. So the first one was about this machine. He said it's different from previous Chinese machines. Of course, it's the first and #1 machine in China that is actually using China's own processors to build it. And the second part is about the cooling, the integration of all these things, and which also impressed me quite a bit when I first looked at this machine. So if you have a chance, I do want to invite you to come over and take a look at the real system. Very beautifully done. We also have a lake, keep in mind, although you can't swim in it. But you can, sort of eat all the different kinds of fish that are produced from the lake. And also, about the software part, we support, I will talk later about the programming model. We support OpenACC to actually, for some parts, you can sort of reduce the programming efforts. And actually, I like his last comment the best. He said, Sunway apparently plans to sell the machine. And apparently, he has made a very good prediction because just 1 week ago at ISC, we actually announced the Sunway Micro, which is sort of a commercial version of this architecture, which you can customize according to your needs. So if you want to order something, you can come and talk to me afterwards. Okay, so that's about the machine. So what is really behind the machine? I'd like to sort of discuss a little bit about the programming challenges we are facing here. So this I made at the ISC conference. I was trying to do some comparison between TaihuLight and some other typical systems, supercomputer systems. So on the left, we have the figure with the hardware numbers. And on the right, we have the figure with the typical benchmark numbers. The TaihuLight is actually this large blue box here. As you can see, the advantage sort of on the computing part is quite apparent. We have a lot more computing power than the other guys. And that's a reason for compute-intensive benchmarks, such as the matrix, the dense matrix operations in LIMPAC, and also the finite difference of finite element methods in HPGMG. We do have good results. And we are also very good at sort of performance per cubic meters, as you can understand for this high density integration we have just introduced. We also have good performance per watt. I mean, at least it was a very good number last year before P-stand with this very amazing P100 power efficiency. So that's about the good part, but also you can see we have some very clear bottlenecks, constraints. If you look at the memory size, so the computing power of TaihuLight is like 10 times more than K computer. But if you look at the memory size, we are roughly the same, or say even slightly less than K computer. And it's the same case for the memory bandwidth. So there's no doubt that we are only the third in HPCG, solving sparse matrices, and also only the second in graph. And in both of them, K computer is still the number one in the world, which sort of shows the advantage in bandwidth in both memory and communication. But we did have a much lower budget than K computer. That's the part I want to mention. So this is the system. Some of the major factors you should think about when you map your application to this computer. It is very large. It's the first system with over 100 petaflops computing performance, first system with 10 million cores. But on the other hand, for the memory, each CPU has only 32 gigabytes of memory, and the memory bandwidth is 136 gigabytes per second. If you convert that into the ratio of compute and bandwidth, that is roughly 22 flops per byte. Okay, what does that number mean? If you look at these most recent many-core processors, like the nice landing of Corey and P100 and P-Stain, the number is around 6 to 7. So you can see in our case, we do have a very, should I say, imbalanced machine. It is very compute hungry and very bandwidth limited. But we also have some hardware differences. For the CPEs, we don't have L1 cache. We have 64 kilobytes of fast buffer, which turns out to be a good number in a lot of the applications that we want to redesign on this supercomputer. And also, we have this very important feature I mentioned, register communication. If you want to do data sharing among different threads within your chip, this is the best way to do it on Sunway architectures. Okay, so the major challenges, of course, the first one, you now have 10 million cores. Okay, when you design your algorithm, you have to keep that in your mind. And then it's memory limited. Okay. Now, in most cases that we deal with, these problems can be fully or partially solved with these new features of this processor I've mentioned. But of course, along the way, you actually have to spend tremendous efforts to refactor, redesign your algorithm, your implementation, all these different kernels to achieve this very good performance. So that's about the challenges. The programming model is pretty much the same as other heterogeneous supercomputers, MPI plus X. We have OpenACC in the middle to sort of reduce some of the efforts when that can be reduced. And then we have the A thread, which you can consider as the CUDA for GPUs, where you basically write your own threading instructions to control every bit of the, sort of the, both the computing part and the memory access part. Now, towards scaling, our approach is a two-level approach. Okay, so normally we allocate 1 MPI process to each of these core groups, as I explained. So in the maximum case, you are dealing with 160,000 MPI processes that can be used for your scientific problem. And then after that, you still have this 65 cores that you can use, were achieved by threading, okay, through either OpenACC or A-thread. So actually, when you design your parallelism, one key point that you have to keep into your mind is that when you design your parallel MPI scheme, you still need to reserve enough parallelism for the 65 cores afterwards. Or in most cases, you actually need to redesign. Okay, you need to redesign your algorithm to actually allocate that extra parallelism for the 65 cores in the CG. The second part is about the memory part, is what we do to achieve latency hiding and also data reuse. The first part is about a carefully designed scheme for your specific application. So you don't want to access the memory from the main memory directly. You need a scheme to do all these different DMA operations to fetch the data from the main memory to your 64 kilobytes fast buffer, and then you do your compute. Okay, so you normally need something like this to overlap your computation and memory operations. And then the second part is about this data sharing, as I mentioned, register level data sharing among different cores. Okay, so that's about the programming part. Now I'd like to give you some, concrete examples, especially in the domain of climate and weather. Okay, so of course that's where the climate started. Even with the first computer, ENIAC, people are starting to write very simple atmospheric models, maybe just 2 levels, and with the resolution of 5,000 miles, something like that, to compute the atmosphere. So that's the starting point of climate models. And then later they find ocean is also to be considered. And then afterwards, of course, they add land and also CIs. So this is pretty much the most normal form of a climate system model, where you have atmosphere, ocean, CIs, land, and also the coupler in the middle to couple all these different things. But this also kind of shows the way. So the model actually develops in the same way with the scientists develop their understanding about the Earth system. So with more understanding, there are going to be more components to be added into this system. So this is what people are trying to do nowadays. And as you can imagine, in China, the atmospheric chemistry part is going to be more and more important, because we have this serious smog issue that we want to deal with. And people are even thinking about, adding the human part, the economic part into this. And all these are calling for more and more computing powers. And of course, people like computer guys, we are always talking about improving the resolution. You want it to be cloud resolving. What was the slogan that people were saying? Resolve each cloud on the sky. I'm not sure whether that is achievable, but that's what people are trying to do nowadays. And also, you want it to be adequate resolving for the ocean part. And all these things ask us for more computing power. Keep in mind, you improve your resolution by 2 times. That's already, at least 8 times in the improvement of the computing amount. And of course, with the fine resolution, your physics parts needs to be, some of them will get removed, right? And some of them needs to be redesigned. And ensembles, So people are nowadays running very large ensembles to improve the accuracy. So this is probably the extreme example. I just had, a few months ago when we had this BDAC workshop in Wuxi, we had this very brilliant scientist from K-Computer. He was doing 10,000 samples at the same time on K-Computer. Now, the argument is that by doing this, he can improve the prediction of sudden rains in the area around K-Computer. But that's the sort of the requirements from the scientists, what they are trying to do, all these different kinds of crazy things. So this figure, I guess, many of you are very familiar with. I borrowed it from NCAR, which shows these different directions are calling for more computing power. So apparently this is something that needs exascale computing capability, right? But if you look from the other side, from the software side, at least this is what we saw in China, okay? We have very good supercomputers, over 100 petaflops computing power. But on the other hand, for the models that scientists really run, they are not capable of taking advantage of these, okay? They are pure CPU programs, and they only scale to hundreds of thousands, of course. And of course, you can see the constraints, millions lines of legacy code that the scientists have accumulated. And they were designed for multi-core, so they are not really suitable for these many-core architectures. So sort of trying to remove all this, to break these walls and trying to take advantage of this new heterogeneous supercomputers in China, we tried to do a few things. So the first thing is trying to develop something from scratch, trying to develop some highly scalable frameworks that can actually use heterogeneous resources and scale to a much larger scale. So this work, we actually started from the year of 2012, where we only have Tsinghua 1A, a CPU, GPU machine. So we designed, and we start from the shallow wave equation. It's a 2D equation. It's much simpler. It's where we start to trying to figure out what's the best way. So we did design from scratch a decomposition scheme that can actually use both CPUs and GPUs resources very efficiently and achieve a sustained performance of 800 teraflops. And in the second year, we expanded to 3D Euler equation to Tsinghua 2, the CPU mic machine, and with a performance of 1.7 petaflops. And we even tried FPGA. We tried to see what can be achieved by designing a fully customized pipeline for this solver. Now, it turns out to be the largest challenge is actually the arithmetic part. Okay, for this simple equation, we have to compute over 1,000 floating point operations in double precision. So at that time, we don't have an FPGA chip that can actually map all this. So what we did was playing with precision. We tried to use a mixed precision to resolve the problem while keeping the same kind of accuracy that the scientists would be okay with. So by doing that, we can achieve very good performance. Even compared with GPU, it's 5 times better. So this one was selected as one of the 27 significant papers of FPL. And I think the even better part is some climate scientists are actually taking a similar approach to their problem, really discuss about the precision, the role of precision in their scientific problems. Okay, so the most recent effort, of course, is on Sunway TaihuLight. And as I have introduced, the first challenge, how do you scale? How do you map this problem into your 10 million cores on this machine? And in this case, actually, for our work on Sunway TaihuLight, we jump from, so previously for GPU, for micro FPGA, we were doing explicit methods. And in this one, we jump to implicit methods. So how do you solve one sparse matrix using all these different cores? So as I mentioned, the first part is about the MPI part. Okay, we have to design something that can actually, use over 160,000 different MPI processes. So what we use is a domain decomposition grid approach. But, as I mentioned, when you do this, you want to reserve enough parallelism for your course. So when we do the multi-grid, we are actually doing a very shallow, very shallow multi-grid. Well, we only have 3 different levels, not, like the 7 or 8 levels people would use for multi-grid in homogeneous architectures. And we also have a uniform domain decomposition, so we have this region that can be what we call plug and play for the subdomain solvers afterwards. So that's the first part to resolve the parallelism at the MPI level. The second part, of course, is more architecture related, is about how to design this subdomain solver afterwards for this 64 CPEs plus 1 MPE in this case. So there are different parts involved in this solver, but the most challenging part is actually this IRU part, which, as you can imagine, is not very parallelism friendly. So what we did was to design a geometry-based pipeline IRU. Our goal is we only want one single sweep of the different elements, and we want it to be free of global synchronizations, and we want to improve the data locality and also data reuse among different threads. So this is what we get. We have 2 different pipelines here. The first pipeline is similar to a lot of GPU approaches. We have each CPE to process this one pencil, one column. And then along this X and Y plane, we are doing another pipeline. So we start from this guy in the corner. After this guy finishes the computation, it will send the results to its 2 neighbors who actually needs its values to start the computation. So each thread will start as soon as they get enough data to compute. Now this communication is of course achieved by the register communication feature I've mentioned, so in a very efficient way. So by doing this, we can then sort of get very good efficient utilization of all these 10 million cores on this machine. So this is some results we have got. As you can see here, for 2 kilometer resolution, which means we have more points, we have more compute for each thread, and our parallel efficiency is 67%. With 3 kilometer resolution, that's 45. And this is the Golden Bear Prize of 2015. That's over 1.5 million cores of Sequoia. The parallel efficiency is 33. They are also using an implicit method. So as you can see here, these numbers are actually pretty good for an implicit approach on this kind of scale. And the other major contribution I think we did last year was actually we compare, as I mentioned, we jumped to implicit methods. So we actually compare our explicit methods and our implicit methods, again, at the scale of 10 million cores. As you can see, this explicit method, of course, has a higher floating point performance, 23, 24 petaflops in double precision. The implicit, 8 petaflops. But if you consider about the simulation speed, sort of how many years you can simulate per day, this guy is actually 90 times faster than this method. Now, of course, this is only for some initial experiments on the mathematical benchmarks. I believe there's still a lot of work we need to do if we want to convert this into a real usable dynamic core, but that at least would give us some insight along the front. Okay, so that's the first part, sort of a design from scratch, something for this very large-scale supercomputer. The second part is actually about the legacy code. The legacy code is actually very valuable. It's developed by many scientists all over the world and over the last 2 or 3 decades. But that also brings the challenge. You want to keep the scientific insights, you have to play with the code. And, a lot of them might still be written in Fortran 77. Very, very difficult to read and understand. So for this one, we had a project actually starting maybe even before the supercomputer was there. In the summer of 2015, we had this team with many professors, students from different disciplines different universities to actually look at the CESM, this Earth system model, and trying to port it onto this Sunway TaihuLight supercomputer. Now the porting part is easy. It's actually just to fix some compiler bugs and trying to make it run on the MPE. The more challenging part is actually the second part. We try to actually refactor and redesign this CAM part to make it really suitable for the underlying hardware architectures. And as you can imagine, this is totally some different challenges from our first work. It's not designing from scratch. You actually have to look at these millions lines of legacy code and no hotspots. Okay, each function is only like 2 or 3% of total time. You have to do it all, otherwise you don't get performance improvements. And it was all designed for the previous generation of hardware, not suitable for the current generation. And more importantly, we don't have people who can understand both the climate and the HPC. We did make some wrong decision. I mean, most of the team, the 30 people we had like 2 years ago, were from computer science. And we had 3 months, very intensive efforts on these Fortran 77 and Fortran 90 codes, And the result was, at the end of the 3 months, only 2 or 3 of the students are still kind of willing to work on the climate problem. Okay. The others, they came saying that I'd like to jump to deep learning, otherwise I can switch to another professor. So, but you can understand. I mean, if you work with some code that you can't really understand, it's very frustrating. So the first step we did was an OpenACC-based refactoring of CAM, and as you can see here, for the dynamic part, we did some manual refactoring, because this part is written by computer guys and easier to understand. But for the physics parts, we were trying to develop some tools that can actually automate this process. So this is the results we get after the refactorization for OpenACC. As you can see, we can scale to the scale of 24,000 MPI processes, roughly 1.5 million cores, with a speed of 2.8 simulated years per day. That's not bad, but just similar to what you can get on Intel. So after that, we tried to push this forward. We tried to do some more aggressive work. So again, we did this A-thread-based fine-grained redesign. So the first step is we rewrite the Fortran OpenACC code to A-thread-C code so that we can have finer memory control with a more specific DMA scheme, and we have more efficient vectorization. And the second, for a lot of the algorithms, we actually redesigned it to achieve better, to remove some of the data dependency and to expose more parallelism. So by doing that, we can then, so this is a figure with the results that we get from different stages. The first column is the result of the original inter-core performance. The second one is after simple porting onto the MPE. The third one is after the OpenACC refactoring. And the last one is with the A-thread design. So as you can see here, the starting point, MPE, maybe 1/10, 1/3. As you can imagine, our core is much simplified. And after refactoring, we can be equivalent or even better than one single intercore. Only after this redesign, you can really get the computing power equivalent to 7 or in some cases 40 intercores. So that's really the performance you can get through redesign. And this is the scaling results. I guess this is probably the first time that we can scale the dynamic core of an existing model to the scale of 8 million cores with a performance of 1.6 petaflops. So I guess I'm probably running slow here. So for WRF, it's kind of similar, as you can imagine, similar challenges that we are facing here. And on top of all this we did for CAM, we also derive a performance model to actually guide our performance optimization afterwards. Consider about the parallelism in compute, parallelism in memory operation, and the extent that you can actually overlap these two parts to estimate the performance that you're getting in the very end. So as you can see here, the first two figures shows the actual performance versus the predicted performance. So as you can see here, this model is actually getting some very good results. And the second one is about, in certain cases, you may not want to use all the 64 CPEs. So in some cases, by using a smaller number of CPEs, you can actually get away with better performance. And this is the sort of the speed up performance we can get. The comparison is comparing 64 CPEs against one MPE. As you can see, most of them are around 7 or 8. Only for compute-intensive parts, you can get somewhere around 14. Now, again, for this part, is here at the stage of OpenACC-based refactoring. Okay, so I'd like to talk a little bit about the long-term plan. As I mentioned earlier, in China, the supercomputer centers are not easy. They have to earn their own money to support the electricity and the stuff and things like that. So the first part is that we're trying to convert the science into service. As I mentioned, the climate weather forecasting, and we also did some work this year, earthquake simulation. So these things we want to work with the national agencies and trying to sort of promote them from scientific discoveries into some services that can be used by the government. Of course, then we can ask them for money to support this machine. And the second part is deep learning. So starting from late last year, we were developing this framework. The first one is what we call a Sunway DNN. It's the low-level parts with high-performance computing functions for the convolutions. The second one is what we call the Sunway Cafe. It is trying to sort of improve the scalability of training really large problems. And this is the performance so far. As you can see, currently we are getting 3.5 times equivalent performance to 24 inter-cores by using one core group. And the last part is, of course, Sunway Micro. So if any of you might be interested, please come to me afterwards. So acknowledgements, Ministry of Science and Technology, which supports this machine and also a lot of the software projects, and RCPC, who actually made this very beautiful machine. And I also would want to thank the friends from NCAR and SCAC who are helping us with the CAM and also the Earth simulation work. Okay, with that I should say thank you. And especially I should thank the organizer. This is the view I had yesterday from the top of the mountain.
Thank you very much, Professor Fu, for this very interesting, inspiring talk. I guess we have questions. Please use the microphone. And
thank you for this very nice talk and overview. I would be interested in your plans on the memory rate. So this 22 byte per flop is of course outside of many of the applications that we're targeting. So what are your plans? And concerning your Sunway Micro, what will be the future of these plans?
The future is, we had this argument actually with the hardware teams from time to time. So actually they know all the constraints of this current architecture and they know all the pains, the software people are having, because we are arguing with them at least twice a week, something like that. So, but now it is a budget thing. You only have this one processor. And keep in mind, I think our technology is probably 1 or 2 generations behind. So with this one processor, you want to fit in the computing power as well as the memory things. So I think that was the reason why they decided they didn't use a much higher bandwidth or L1 cache for the CPEs. For the next generation, as far as I know, at least the buffer is going to be doubled. And maybe there's going to be some kind of cache facility, but we don't know for sure yet. The bandwidth, of course, they are starting to look at the stacked memory things similarly to other architectures.
Okay, is there one more? Please raise your hand. Yeah, there's one question.
Hello, thank you for this very impressive results on CAM and WRF. And my question is about precision. What sort of constraints or restrictions did you have on precision, and what were your observations for that?
Well, actually, in these two projects, we didn't play with precision that much because that's actually one constraint of Sunway architecture for now. We focus too much on double precision. So if you switch to single precision, we don't have too much performance benefits. So in these cases, we are just using double precision for CAM, and in most cases, single precision for WRF.
Okay, so there's one more question. Joost.
So I have a question on your software refactoring efforts. You have put a very large team of 30 people working for many months on the code. But if you go to the next architecture, is this work lost? And in this context, would it be interesting to have, for example, a DSL for this dynamical core that could be just retargeted to a new architecture?
Yes, definitely. I mean, we are trying very hard to actually push students to move the efforts from the specific application towards tools or even compilers. But you probably understand how hard it is to persuade a student to work on compiler, things like that. But that's actually our plan. I mean, after all these results, we would want to convert them into actually a tool that can benefit other scientific applications as well.
Okay, is there one more question? I cannot see anyone. So in this case, let us thank again Professor Fu for a very nice talk.
Thank you.